Hello and welcome. This is going to be a very gentle video suggestive of fascinating mathematical realms up ahead. So this is going to be another measure of infinity, but I'm actually not even going to really define the measure. I'm just going to kind of show you a little something related. So here I have what's called an ordinal number. It's going to be this particular ordinal is the set of all the natural numbers, 0, 1, 2, on forever. And the way I think about it is 1 comes after 0, 2 comes after 0 and 1, and so on, so that these are ordered. And then I have another ordinal here, which is omega times 2. This one has all the natural numbers, but then after all of those we have omega, which is going to be larger than any of the natural numbers. And then omega plus 1 is even larger than omega, and omega plus 2 is even larger than omega plus 1, and these go on forever. So it's kind of like I have all the natural numbers here, and then I have like a copy of the natural numbers that comes after the natural numbers. That's the times 2. So I've kind of got 2 copies of them. Let's go over one more example. So this is omega squared. So here I have the natural numbers. Then I have a copy of the natural numbers that comes after all of these. And then I have a copy that comes after all of these. And I keep doing these copies sort of on forever in that omega kind of way. So I got the 0th list, the first list, the second list, on forever, sort of like that. Now, if you look back at this one, notice that I can give all of these a natural number name, a unique natural number name. Obviously, this one I can call 0, this one I can call 1, this one I can call 2. I'm going to consider 0 a natural number for this video. I can also give all of these a unique natural number name. I could call this 0, this 1, this 2, this 3, this 4, this 5, and in that kind of bouncing back and forth way, I can give them all their own name from the natural numbers. That means this is countable. And in the same way, omega squared, even though it looks like a lot of elements in here, it's also going to be countable. I can name this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then just keep going on the diagonals like that, and in that way I give every single element in here its own unique natural number name. So this is a countable set. And these are also ordinals. So we have omega times 2, and omega squared are all countable ordinals. Because while they do have a lot of elements in some sense, we can essentially, name them all with the natural numbers, and it's all going to be fine. So let's let omega 1 be the set of all the countable ordinals. And I claim that this set is going to be uncountable. First of all, omega 1, if it was countable, would then... See, if omega 1 was countable, and it has all the countable ordinals inside of itself, then by it being countable and having all the countable ordinals inside itself, it would belong to itself. It would be inside itself, and that is going to lead to a contradiction with the concept of ordinal. An ordinal cannot be greater than itself, because for reasons that I'm not going over in this video. So omega 1 is going to be the set of all the countable ordinals. So you see it's got 0 in there, omega in there, it'll have omega times 2, it'll have omega squared. Of course, omega squared is going to come after omega times 2. And it goes on forever, and by forever I mean a very abstract forever that you cannot explain. It goes on forever, okay, in an interesting way. That kind of defies an attempt. It defies an attempt to sort of define this recursively. And here's a really interesting thing about omega 1, is that if I had an increasing sequence, a strictly increasing sequence of ordinals, all less than omega 1, could I have it to where the sequence of ordinals converges to omega 1? And the answer is no. Omega 1 is an interesting ordinal. It's uncountably infinite, and if you're trying to kind of build up to it in steps, so you start at 0 and then you sort of go up a step, and by up a step I mean as far as you want to go in that single step, as long as you're not like jumping straight to omega 1 or past omega 1. You have to stay, we're strictly having to stay below omega 1. So you do that first step as far as you want to go, as long as you're still below omega 1. And then you do your second step as far as you want to go, but staying below omega 1. And then you do your third step. And then you do your fourth step. And you keep doing this infinitely. And by infinitely, I mean, you know, a sequence. So you have your 0th step, your first step, your second step, your third step, and it goes on like that forever. And no matter how you do that, no matter how big you try to make each step, no matter how you try to pattern it out or not pattern it out, abstractly define it, no matter how you do that, the sequence is not going to make it up to omega 1. Omega 1 can't be built in a countable number of steps from below. That is a different sense of sort of size that it has. We're not talking about how many elements it has. We're talking about, at minimum, how many steps from below does it take to build up to the thing. It's a different kind of size of infinity in a sense, a different notion. It's called cofinality. But that's gonna be it for this video. I hope you found it interesting. If you have any questions, then, you know, I can try to answer them. Thanks and take care.